Before we dive into robotics theory, let's start with a relatively simple example. And this example will help us understand some of the key tasks that we typically need a robot to do. So we will start by discussing what is called a planar elbow manipulator robot. So obviously it's a robot. Manipulator means it's a robotic arm. And what does planar elbow manipulator mean? We'll see that in a second. But this is also called a 2R planar robot. And to explain what is 2R, first we will have to look at two most common types of robot joints. And those are revolute joints and prismatic joints. So two most common types of joints in robots: revolute, which means at the joint there is a relative rotation between two links, and typically we call that R. So 2R means two revolute joints. A robot having two revolute joints, and that is planar, is called a 2R planar robot. And the other type of robot joint that is also quite common but a little less common than revolute joint would be prismatic joint. And this we refer to with the alphabet P. Prismatic joint means there's a relative extension or compression between two links. So two links sliding over one another, or two links moving away from each other in a linear fashion would be a prismatic joint. Okay, so let's get down to drawing a schematic and see what's going on with this 2R planar robot. So let's say the ground hinge point or joint is over here. Let's call it O1, and there are two links. First link I'm drawing over here, and then there is a second link that I'm drawing over here. And these, let's say, have link lengths L1 and L2. They are simply the lengths of these links. And the first joint is O1, the second joint is O2, and these are both hinge joints or revolute joints. So we have seen this in basic mechanics courses. But here, when you're talking about a robot, you would actually have a motor sitting at each of these joints that makes it rotate, right? So there's a motor at O1, and that's a revolute joint, and there's another motor at O2, and that's a second revolute joint. Now we also have to now define angles. So the first angle, let's call it Q1, and the angle of the second link, let's call it Q2. And there's one point here to note which can be confusing, and when you go to the hardware, you will see that it does make a difference how you define this. And that point is the convention of the second angle. This angle is defined relative to a horizontal which is inertially fixed, right? This seems very natural because in most of the trigonometry theory and trigonometric problems, this is how we define angles. But when it comes to robots, you will see that this is somewhat of an unnatural definition, and we'll talk about that a little bit later. At the moment, we don't need to worry about it. So Q1, Q2, and in different textbooks, different resources, of course, you will have different alphabets. Sometimes you would call them theta 1, theta 2. Sometimes you would even see P1, P2, but Q1, Q2 or Qs are by far the most common notation used for robot joint angles. Now the other important thing for us over here, now everything is in a plane, that's why it's a planar robot, and you can sort of see that it looks like an elbow here, so elbow manipulator. But the other thing that's important for us is the end tip coordinate, right? So let's say the end tip point is P and its coordinates are x comma y, right? You can think of having an x and y axis over here at the origin, and P would have a certain x coordinate and y coordinate relative to this origin, right? And there is another common name for P or any end tip of the robot, and that is called the end effector. So end effector of a robot, sometimes it is called EE, and if we just say x, y coordinates of a robot, we typically mean the coordinates of the end effector. So Q1, Q2 are joint angles, and as I said, we have defined them as absolute angles, angles relative to an absolute horizontal. And with this framework, let's define three very simple tasks that we want this robot to do, right? So there are three tasks. Task 1, no matter what the motor does, it rotates the joints by a certain amount. You always want to be able to calculate what is the end tip doing. So you want to calculate the end tip coordinates and end tip velocity. So task 1 is calculate end effector. So let me call it EE. Let me use capital EE so that there is no confusion. Calculate end effector position and velocity given any arbitrary motor actions, right? So given arbitrary motor or joint motion. Okay, that is the first task. It sounds simple enough. Task 2, let's see if we can do the reverse, right? Given an arbitrary desired end tip position, figure out what the motors need to do to go there, right? And we can make that a little bit more complicated, and we can say given an arbitrary end tip trajectory. What is a trajectory? Essentially x and y coordinates as a function of time, right? So I have a time trace of what x and y coordinates of the end tip should be, and I want to figure out what the motors need to do for the robot to be able to achieve that. So given arbitrary end effector trajectory, I would say x and y as functions of time. You want to be able to calculate required motor or joint motion. And the third task, this may seem a little unnatural at the moment, and as you go along and do more and more robotics problems, you will see that this is quite common. You will have this requirement every once in a while. And this is given an arbitrary location of a wall with certain orientation, the robot end tip should go touch that wall and apply a specific force against that wall. So that is our third task. So given an arbitrary location and orientation of a wall, make the robot reach the wall and apply a pre-specified force. Or to keep it simpler, let me say apply a prescribed force. Now to do this, we will start with the assumption that the motors have the capability to provide any arbitrary angle or any arbitrary torque, right? So if we want a certain angle, we will at this moment assume that the motor will be able to give us that angle. We will not worry about how the motor achieves that rotation. And likewise, if we want a certain torque at each of these joints, at the moment we will assume that the motors can give me whatever torques I want, right? And later on, when we get into control and other aspects, we will see how to get the motor to achieve a certain angle or a certain torque. But at the moment, we will assume that is possible. So assume motors have the ability to provide any desired angles Q1, Q2 or torques tau 1, tau 2. Now why would we ever need torques? As you can imagine, in task 3 we want to apply a force against the wall, and for that you can imagine that you will not start to think about what kind of torques will be needed at the joints to apply that force. Okay, before we go further, now these 3 tasks have they are relatively simple for this example, but they give you an idea of the kind of task that you will ask a typical robot to do. And we will not develop general theory at this moment. We will just see how to solve these 3 tasks with this particular example. But later on, you will see for each of these, we will develop a general robotics theory that you can apply to any robot. Okay, so before we go further, now let's go to the robot and let's have a look at some of these things in a little bit more detail. Okay, here we are. Now, as you might have noticed already, this is really not a 2-hour robot. It is indeed a planar robot. Everything is in one plane. Of course, there is some thickness to the robot, but you can really imagine everything is everything is happening in one plane. But here, very clearly, you see there are 3 revolute joints. So there are 3 motors that can that operate 3 different links. This is really not the same as a 2-hour robot, but what we can do is we can lock this 3rd joint and imagine this whole link to be a single link. So therefore, in effect, we have only 2 joints over here with 2 motors operating them. And as we just discussed, our assumption is any angle that we need here, we should be able to ask the motor to give us that angle, and the motor should be able to rotate to that angle. Now, if we can also note a couple of more things, the x-axis is here, y-axis is here, the origin is here. So when we defined Q1 against a horizontal, it was really this angle respect to x. And when we said the second joint has angle Q2, that's again relative to this horizontal, and this is an absolute angle. Now, why did I say this is unnatural for a robot? Because typically you are measuring at the joint, and the robot or rather the motor has no way of knowing where the inertially fixed x-axis is. So it is always measuring, so you would have guessed it already, it is always measuring a relative angle, which means it's measuring relative to where it started, how much it has rotated. So all your robot measurements, particularly at the other joints, at the base joint usually it's not a problem because it's relative to a fixed base, so that is either you do relative or absolute, it's the same angle. But at the other joints this can be a challenge, so keep track of relative angles and absolute angles, and we will talk about this later on. And in this case, just one last thing to note is that P over here is the end tip here. right? So when I say end effector coordinates, in this particular case, literally it's the point over here. If I now remove the robot here, so it's the x coordinate and y coordinate here that we are talking about. So in the first task, we want, no matter what the two motors are doing, we want to precisely calculate the end effector position. In the second task, given end effector desired position, we want to know what both these motors need to do to make the robot reach here. And in the third task, if I have a wall here and I want the robot to reach there and go apply a force, then I want to figure out what to tell the robot. Okay, let's go back to the theory and see how to solve this. Okay, back to the board. We had three tasks. First, let's start with the first task, where given arbitrary robot, or rather motor actions, we want to calculate the end tip position and velocity, and that, you might have guessed, it's relatively straightforward trigonometry. So we want to know what is x and what is y given q1, q2 and q1 dot and q2 dot, and we can apply trigonometry right away. And I believe all of you can do this in few seconds in your head already, right? So x coordinate of the end effector would be L1 cosine q1 plus L2 cosine q2. So L1 cosine q1 plus L2 cosine q2. And likewise, y coordinate would be L1 sine q1 plus L2 sine q2. And since we'll be seeing a lot of sines and cosines, we can use a shorthand notation to represent cosine and sine. So let's write this as L1 CQ1 meaning cosine of Q1, plus L2 CQ2, and the second y coordinate as L1 SQ1 plus L2 SQ2. That's it. It's as simple as that, end effector coordinates in terms of the joint angles. Now we can differentiate these to find the velocities. So we get x1 dot, which is the x component of velocity of the end effector. That would be minus L1 SQ1 into Q1 dot minus L2 SQ2 into Q2 dot, and y dot would be similarly L1 CQ1 into Q1 dot plus L2 CQ2 into Q2 dot. And these together can help you calculate end effector position and velocity in just a couple of steps. Now what we would do, and you will see this is very useful as we go to more general robots, is try and write this in matrix form. So let's do this. So x1 dot and x dot and y dot, which are nothing but components of the velocity, or x and y components of the velocity of the end effector. Now I would write it as minus L1 SQ1 minus L2 SQ2, L1 CQ1 and L2 CQ2, the whole thing multiplied by Q1 dot Q2 dot. And let's call this equation 1 and let's call this equation 2. And as you would have noticed, this is a nice organization of the velocity relationship. What is happening here? Given how fast the motors are rotating, you can multiply it by some matrix. This matrix depends on the current configuration of the robot. In other words, the current joint angles Q1 and Q2. And when you multiply this out, you get the end effector velocities, right? And between 1 and 2, you can solve task 1. And there is a name for this. This is nothing but forward kinematics of a robot. And you can be a little bit more specific This is forward position kinematics, and equation 2 where you are relating the velocities is forward velocity kinematics. And why is it called forward kinematics? Because given motor actions or motor motions rather, you can calculate what is happening at the end effector. And if you're doing position, it's position kinematics. If you're doing velocity, it's velocity kinematics. Great. So this is task 1. Now we have to talk about task 2, which is a little bit more involved. It's a little trickier than task 1. Ready? Okay. In task 1, we saw given arbitrary motions at the joints Q1, Q2, and Q1 dot and Q2 dot, we figured out how to calculate x, y, end effector coordinates and end effector velocity components x dot and y dot. Now in task 2, we need the exact opposite of this, right? So given end effector positions, we want to find out what the motors need to do, what Q1 and Q2 should be. So task 2 need inverse calculation of task 1. So task 1 we said has a name, it's called forward kinematics. So this, then you might have guessed, obviously has inverse kinematics as the name, because you are now doing the inverse calculation. Now what you can do is use the same two equations, equations 1 and 2, and solve them numerically to find Q1 and Q2 given x and y. So let me say there are 3 ways to do this. So first one is solve 1 and 2 numerically, and that is not very convenient in many situations. Remember, for a typical robot task, you need to be able to do this at every time step. While the robot is moving, at every instant, you need to be able to calculate what the next step Q1 and Q2 should be, or what the motor should be doing in the next time instant. So anything that is numerically, computationally intensive, which can take time to compute, is not a very elegant solution, especially when you are dealing with relatively long trigonometric relationships. Now remember, if you had multiple links here, you would have those equations have several sines and cosines. So you can do this, but not the best way. The other way is if you had a closed form solution. What is a closed form solution? It means you have an equation for Q1 and Q2 explicitly in terms of x, y, x dot, y dot, without you having to do any further integration, differentiation, or any other solving. This would be, of course, the most convenient. But in the general case, this is difficult. This is not always feasible. But fortunately for us, for 2-hour manipulator, this is something that we can easily do, and we will do that in a second. There is a third approach, which is again a numerical approach, but a slightly different numerical approach as compared to what I mentioned in one. And this, it turns out, is the most commonly used approach today in industry, and we will talk about this sometime later on. But for a 2-hour manipulator, let's see if we can work out a closed form solution. So to work out a closed form solution, we will need to do some trigonometry. So let me draw a couple of triangles there, and then do, apply some trigonometric identities to figure out expressions for Q1 and Q2. So first triangle, let me draw the same two links. So this is L1, L2, and this coordinate is x, y if this is the origin, right? And now let me complete this triangle. This is now an obtuse angle triangle. The length of the blue hypotenuse is nothing but, using the distance formula, square root of x squared plus y squared, right? So if I want the square of the hypotenuse, I'll get x squared plus y squared. Okay, let me also define a new angle here, theta, and theta is nothing but second joint angle, but measured in a relative sense, relative to the first link, right? So we just talked about the fact that here we have defined it Q2 as an absolute angle, and it is not very natural. We would in many cases want to switch to a relative angle. For the moment, let me still keep Q2 as the absolute angle and then just define this angle theta. So this is one triangle. Now here we can calculate theta using cosine rule. I'm sure all of you have forgotten what is cosine rule. It's nothing but Pythagoras theorem, but applied to triangles that don't necessarily have a right angle in them. So in this case, this is an obtuse angle triangle. So if you remember, cosine rule is nothing but hypotenuse square is equal to first length squared plus second length squared minus 2 times length 1 into length 2 into cosine of the angle between them. So in this case, the angle between them, which is the obtuse angle, is 180 degrees minus theta. So I can switch to theta and get a negative cosine theta. So cosine of 180 minus theta is negative cosine theta, and from that I can calculate theta. So here I would get theta is equal to cosine inverse hypotenuse squared is just x squared plus y squared, as I just talked about, minus L1 squared minus L2 squared divided by 2 L1 L2. Okay, so this is my first expression for theta. Now I need to draw another set of triangles to be able to go from theta to Q1 and Q2. So for that, let me redo the same thing, but now so this is still xy. Now let me complete the red triangle here, where again the hypotenuse of the red triangle is x squared plus y squared, the square of the hypotenuse, but the vertical over here is just y and the horizontal is x. And let me also draw a blue triangle which is extending this first link until you hit a perpendicular from the end effector. So I hope you can see, we will first look at red triangle, then blue triangle, and use the red triangle to calculate this angle beta, and use the blue triangle to calculate this angle gamma. And as you would have guessed already, your Q1 over here is nothing but beta minus gamma, right? So this is now relatively straightforward triangle identity. So beta is tan inverse of y over x, and gamma is tan inverse of opposite over adjacent. Opposite is L2 sine Q2, so tan inverse of L2 sine Q2 divided by, or rather sine theta divided by adjacent is L1 plus L2 cosine theta, so L1 plus L2 cosine theta. So this gives me Q1, and when I know theta and when I know Q1, then my Q2 is straightforward. It is simply Q1 plus theta. So these two equations give me a closed form expression for Q2 and Q1 when I know x and y. So this is task 2. As I said, when you have many more links and when you have three-dimensional geometry, this is not always feasible, and we will have to resort to 1 or 3, and we will talk about those later. But for the time being, we are satisfied with this, and this gives you an idea of inverse kinematics for 2R or planar elbow manipulator. In task 3, what we needed to do was given a location of a wall and a certain orientation of a wall, we wanted the end effector to reach that wall and apply a certain force against it. So let me draw a quick diagram of how that might look like. So let's say, let me take blue for the wall. Let me say there is a wall right here, and I wanted the end effector to maybe reach this point and then apply a normal force against that wall, and it's a force that is given to you by the user. In this case, you might be the user yourself. And if you are applying a force F on the wall, then you are getting an equal and opposite reaction from the wall. And the task here is to find out what the motors need to do, or more specifically, what torques the two motors will need to apply to sustain a force F against the wall in a static situation. There is no motion. Once it touches the wall, it just stays against the wall and then applies a force F. Then how do you calculate tau 1 and tau 2? That's task 3. And it must be obvious, this you resort to free body diagrams. So let's draw two free body diagrams. One is free body diagram of link 1, and the second, let's draw free body diagram of link 2. Okay, so before we draw a free body diagram, let's imagine, so force F will have x and y components. So at the end effector, you will have an Fx and then Fy. So for the free body diagram of link 2, I have at this joint tau 2 is applied, and at the end effector I have a Fx and Fy, which are just components of F, and there would obviously be reaction forces at this joint, but we may not need to know those at the moment. Let me just draw those arrows, but let me not worry about what they are at the moment. Right. Okay. Now free body diagram of link 1, I do the same thing for the first link, and I would get again something very similar, tau 1. Here I need to know what are the reaction forces at the end of link 1, and for that I may have to now worry about what these black arrows are. If this is in static equilibrium, there are no other vertical forces acting on it other than Fy and this reaction, then this reaction will have to be equal and opposite to Fy, and the reaction applied by link 2 on link 1 would be equal and opposite of this. So essentially, since everything is in static equilibrium, you will get literally, and this is no surprise, you will get literally Fx and Fy, which is being felt by the end effector at a different location, at a different orientation. You will get the same reaction forces at the end of link 1 as well. Right. It's a little obvious once you think about it, but when you first work it out, it's like, really, is it true? Different orientation, different location, but still same forces. Here again, you will have reaction forces, but that doesn't matter to us. Now what do? Remember, we want to calculate tau 1 and tau 2. Right? So we want to calculate torques. These are both in static equilibrium. So going back to first year engineering or even 11-12 standard. So we do really static equilibrium means sum of moments is equal to 0, and the most convenient way for us to take moments is about O2 and about O1. So sum of moments about O1 is equal to 0, and this would give me, if I take counterclockwise positive, this would give me tau 1 and minus Fy L1 cosine theta, or rather cosine Q1, sorry, it's not theta, Q1, and plus Fx L1 sine Q1 is equal to 0, or in other words I can write tau 1 is equal to Fy L1 cosine Q1 minus Fx L1 sine Q1. This gives me a direct expression for what the joint torque or the motor torque at joint 1 needs to be to apply this force against the wall. And with free body diagram of link 2, I do sum of moments about O2 is equal to 0. Again, trivial stuff. We have done this over and over again in our 12th and first year engineering. So I would get something very similar again. Tau 2 is equal to, or okay, I can skip this step and then directly go to tau 2 is equal to Fy. I would get an L2 cosine Q2 minus Fx L2 sine Q2. And these two equations, really these two equations are the equations that we care about. So these two together, let's call them equation 4, and they tell me for a specified force F what the joint torques need to be, and this is for statics. But there's something interesting going on over here. One, this is only true when the robot is not moving. When the robot is moving, a lot more things come into the picture. And the other thing that is interesting is if you write this now in matrix form, where you take Fx and Fy out as a vector and everything else as a matrix, this matrix starts to look very similar to your equation 2 in task 1. It's not the same, but it does look very similar. And it's not a coincidence, there is a relationship between velocity kinematics and force statics, and you will discover that later on when you start doing more of this. So this completes 3 tasks. It's relatively straightforward with trigonometry to do all 3 tasks, but this is not what we want to do for all other robots, because I don't know about you, but I will not have the patience to draw lots and lots of triangles if I have 7 links with 7 angles and 3-dimensional angles. I'm not good at visualizing 3-dimensional angles. So we need something that's relatively simple to apply and something we can code up so that we don't have to redraw and reapply these identities over and over again. So that's what the rest of the theories in robotics do. They look at some of these in a much more general perspective, use mathematical formulations that you can simply automate and code up, so it can be applicable for any robot. So that's where we will go next.